You are sitting still right now, or at least you believe you are. Your body feels the pressure of the chair beneath you, the weight of your hands on your desk, the familiar tug of the earth holding you in place. You have felt this sensation your entire life. Every single day, from the moment you took your first breath, you have been pulled toward the ground. But what if I told you that you have never once been pulled anywhere? What if the force you feel right now, this heaviness pressing you into your seat, is not the earth pulling you down at all? What if it is something else entirely, something pushing you, something accelerating you upward at this very moment? What if everything you believe about why you stick to this planet is a comfortable fiction, a story told so many times that it became indistinguishable from truth? This is the story of how one of the greatest minds in human history discovered that gravity, the most familiar force in the universe, is not what we think it is. And it is the story of why that discovery changes everything about how you should understand your own existence. There is a moment in every child's education when they learn about gravity. A teacher tells the familiar tale: Isaac Newton, an apple, a tree, the flash of insight. And then they are handed an equation: F equals G times M1 times M2 divided by R squared. Force equals mass times the pull of attraction. You learn that the earth is pulling you, that the sun is pulling the earth, that every object in the universe reaches out across the void of space and tugs on every other object. You learn that this invisible rope of attraction is what holds the cosmos together. And that is where the lie begins. Do not misunderstand. Newton was a genius, one of the greatest intellects in human history. His law of universal gravitation revolutionized our understanding of the cosmos. For over 200 years, his equations predicted the motions of planets with astonishing accuracy. They guided ships across oceans. They predicted the existence of Neptune before anyone had seen it. They eventually guided rockets to the moon. Newton's gravity was not wrong in the sense that it failed to work. It worked beautifully, but it was wrong in a deeper sense, in the sense that it described what gravity does without ever explaining what gravity is. Newton himself knew this. It troubled him deeply. In his private letters, hidden away from the public pronouncements that made him famous, he confessed his discomfort with his own theory. In a letter to the classical scholar Richard Bentley in 1693, Newton wrote something extraordinary. He said that the idea of gravity acting at a distance through empty space without any material cause was to him so great an absurdity that he believed no person who had a competent faculty of thinking in philosophical matters could ever fall into it. Read that again. The man who invented the theory of gravitational attraction called his own theory an absurdity. Newton described what happens when you drop an apple. It falls. He described how fast it falls. He described the mathematical relationship between the apple's mass, the Earth's mass, and the distance between them. He could calculate with stunning precision exactly where that apple would be at any moment during its fall. But he never explained how the Earth knows the apple is there. He never explained what reaches across the void between them and tugs. He never identified the mechanism, the connection, the invisible hand that links two objects separated by empty space. For over 2 centuries, physicists simply ignored this question. They learned Newton's equations, used Newton's equations, taught Newton's equations to their students. And they pretended the mechanism did not matter. It works. Who cares how? But one person cared, and he would spend years, nearly a decade of his life, wrestling with the question that Newton had avoided. In 1907, a 28-year-old patent clerk named Albert Einstein was working at the Swiss Federal Patent Office in Bern. He spent his days evaluating patent applications, deciding which inventions were novel enough to deserve protection. But his mind was rarely on patents. 2 years earlier, in 1905, Einstein had published 4 papers that would change physics forever. One introduced the special theory of relativity. Another explained the photoelectric effect, work that would eventually earn him the Nobel Prize. A third provided definitive evidence that atoms exist. The fourth introduced the most famous equation in science, E equals mc squared. By any reasonable measure, Einstein's 1905 papers had already secured his place in history. But he was not satisfied. Something was missing. Special relativity had established that nothing, not even information, could travel faster than the speed of light. This was not just a speed limit. It was a fundamental feature of reality. Causes must precede effects. Information must propagate from here to there. Nothing can happen instantaneously across a distance. But Newton's gravity worked instantaneously. According to Newton, if the sun suddenly disappeared, the Earth would instantly fly off in a straight line. The gravitational pull would vanish the moment the sun did. But the light showing the sun's disappearance would take 8 minutes to reach us. For 8 minutes, we would see a sun that no longer existed, no longer exerted any gravitational influence. This could not be right. Either Newton was wrong, or special relativity was wrong. Both could not be true. And then, sitting at his desk in the patent office, Einstein had what he would later describe as the happiest thought of his life. He imagined a man falling from the roof of a house. In that moment of falling, what does the man experience? What does he feel? Einstein realized something profound. The falling man would feel weightless. If he released an object from his hand, it would float beside him. If he tried to stand on a scale, the scale would read 0. Every sensation of gravity would vanish. If a man falls freely, Einstein realized, he would not feel his own weight. Think about that for a moment. Think about what it means. Astronauts floating in the International Space Station appear to be weightless. They drift through their modules, tumbling and spinning as if gravity did not exist. But the space station is not beyond Earth's gravity. Far from it. At the station's altitude, about 400 kilometers up, gravity is still 90% as strong as it is on the ground. The astronauts are not floating because they have escaped gravity. They are floating because they are falling. The station is falling toward Earth, constantly, perpetually, and so are the astronauts inside. They are all falling together at exactly the same rate, following the same curved path around the planet. And when everything is falling together, the sensation of gravity completely disappears. This was Einstein's crucial insight. If you cannot feel gravity while falling, and falling is supposed to be what gravity makes you do, then what exactly is gravity? The answer would take Einstein 8 more years to work out. 8 years of struggle, false starts, mathematical dead ends, and moments of despair. But the core idea was there in that moment, at the patent office. Gravity is not a force pulling you down. It cannot be. A force you cannot feel is not acting on you at all. To understand what Einstein discovered, we need to abandon some deeply held intuitions. We need to understand what physicists mean by space-time. You already know what space is. It is the three-dimensional arena in which you move. Up and down, left and right, forward and back. You can walk through it, travel through it, exist within it. You can point to locations in space and describe how far apart they are. Time is something you move through as well, though in only one direction. Forward, always forward. From past to future, moment by moment, heartbeat by heartbeat. You cannot stop moving through time. You cannot go backward. You can only proceed relentlessly toward the future. Einstein's special relativity revealed something shocking about space and time. They are not separate things. They are woven together into a single four-dimensional fabric, a unified entity that physicists call space-time. Every event that happens somewhere in space-time. When you were born, that was an event with specific coordinates, a location in space, perhaps a hospital room in a particular city, and a moment in time, a specific date, a specific hour. Those four numbers, 3 for space and 1 for time, pinpoint your birth in the fabric of reality. And here is where it gets strange. This fabric of space-time is not rigid. It is not a fixed background against which events happen. Space-time itself can bend, it can stretch, it can warp, it can curve. And the thing that warps it is mass. Picture a heavy bowling ball placed on a stretched rubber sheet. The ball creates a depression, a curve in the sheet. If you roll a marble across the sheet, the marble's path will curve as it approaches the depression. It will spiral toward the bowling ball, not because the bowling ball is reaching out and pulling it, but because the marble is following the curved surface of the sheet. This is the analogy that physicists use to explain curved space-time. And it is a decent starting point. But it is incomplete in an important way, because space-time is not just curved in space, it is curved in time as well. The curvature of time is actually more important than the curvature of space for understanding why you stick to the Earth's surface. Near a massive object like the Earth, time runs more slowly. Not by much, not in a way you would notice in everyday life, but measurably, provably. Time at the top of a mountain passes slightly faster than time at sea level. Time at the Earth's surface passes slightly more slowly than time in orbit. This is not science fiction. This is measured fact. We have clocks precise enough to detect these differences, and we rely on them constantly. Your GPS navigation would be useless if it did not account for the different rates of time at different altitudes. Now here is the key insight. The American physicist John Wheeler, who worked with Einstein in his later years and became one of the greatest relativists of the 20th century, summarized general relativity in a single sentence that has become famous. Space-time tells matter how to move. Matter tells space-time how to curve. There is no pulling in this picture. There is no reaching across the void. There is no invisible rope of attraction connecting massive objects. There is simply geometry. The Earth's mass curves the space-time around it. You, existing in that curved space-time, follow the straightest possible path through it, and the straightest possible path through the curved space-time near Earth leads downward toward the planet's center. But here is the terrifying part. You are not following that straightest path right now. You are being prevented from following it. The ground beneath your feet, the chair beneath your body, the floor of whatever room you are in, is stopping you from taking your natural path through space-time. And that stopping requires a force, a real physical force, a force you can feel. That force is what you call your weight. In curved space-time, the straightest possible path is called a geodesic. Think of how an airplane flies from New York to London. If you look at the flight path on a flat map, it appears curved, bending northward toward Greenland before arcing back down toward England. But on a globe, that path is actually the shortest distance between the two cities. A great circle, the straightest possible line on a curved surface. Geodesics in space-time work the same way. They are the paths that objects naturally follow when nothing is interfering with them, when no force is acting on them, when they are simply allowed to move freely. And here is the revolutionary insight of general relativity, the insight that overturns everything you thought you knew about falling. When you are in free fall, when you are falling through space with nothing to stop you, you are following a geodesic. You are taking the straightest possible path through curved space-time. And because you are following that natural path, because nothing is interfering with your motion, you feel no force at all. You are weightless, not apparently weightless, not feeling weightless while actually being subject to a force, actually weightless, actually free of any force, actually taking the natural, unimpeded path that the geometry of space-time dictates. But when you stand on the Earth's surface, the ground interferes. The solid rock beneath your feet, held rigid by electromagnetic forces between atoms, prevents you from following your natural geodesic. It stops you from falling. It blocks your path. And to block your path, to hold you in place against the curvature of space-time, the ground must push. That push, that force from the ground shoving you upward, accelerating you away from your natural trajectory, is what you feel as weight. Let that sink in. Your entire life, you have believed that gravity pulls you down, that you feel heavy because the Earth is attracting you toward its center, that there is a force called gravity reaching up through the ground and tugging on every atom in your body. But according to Einstein's theory, the exact opposite is true. You feel heavy because the ground is pushing you up. The floor beneath you is accelerating you away from your natural path through space-time. You are being constantly, perpetually, every moment of every day pushed upward by the solid matter of the Earth. And that sensation of acceleration, that resistance to your natural motion, is what you experience as weight. Gravity is not pulling you down. Gravity is the curvature that defines what down means. Your weight is the force required to keep you from following that curvature. You have been misunderstanding your own body your entire life. Now, this sounds like philosophy, like wordplay, like the kind of semantic game that physicists play to make themselves feel clever at cocktail parties. Does it really matter whether we say gravity pulls us down or the ground pushes us up? Is there any real difference? Yes, there is, and we can prove it experimentally. The proof began in 1859, long before Einstein was born. A French mathematician named Urbain Le Verrier, famous for predicting the existence of Neptune from perturbations in Uranus's orbit, turned his attention to Mercury. Mercury's orbit was not quite right. As the closest planet to the Sun, Mercury should follow a simple elliptical path. And it did, mostly. But the ellipse itself was rotating. The point where Mercury came closest to the Sun, called the perihelion, was slowly precessing, moving around the Sun in a circle. Most of this precession was explained by the gravitational influence of the other planets pulling on Mercury as it swung past. But not all of it. There were 43 extra arc seconds of precession per century that Newton's theory could not explain. 43 arc seconds per century. That is a tiny amount. An arc second is 1/3600th of a degree. 43 of them per century means Mercury's perihelion was shifting by about 0.012 degrees every 100 years. This is not something you would notice by looking at the night sky. This is something you would only find by comparing extremely precise astronomical observations made decades apart. But Leverrier found it, and it drove him crazy. He tried everything. He proposed that there was an undiscovered planet, which he named Vulcan, orbiting even closer to the Sun than Mercury. He suggested that the Sun might not be perfectly spherical. He considered the possibility of interplanetary dust. None of these explanations worked. The anomalous precession of Mercury remained a mystery for over 50 years. And then, in November 1915, Albert Einstein completed his general theory of relativity and applied it to Mercury's orbit. The answer came out to 43 arc seconds per century. Einstein later recalled that when he saw this result, he was beside himself with joyous excitement for several days. The mysterious precession, the discrepancy that had plagued astronomers for half a century, fell directly out of his equations. No adjustments needed, no free parameters to fiddle with, just the natural consequence of curved space-time. Newton's theory said gravity was a force pulling on Mercury, but that force, however you calculated it, could not explain the precession. Einstein's theory said space-time near the Sun was curved, and that curvature, applied to Mercury's orbit, predicted exactly the observed motion. The math was clear. Newton was wrong. Einstein was right. But Mercury's orbit was just the beginning. Einstein made other predictions, more dramatic predictions that could be tested directly. One of them involved light. In Newton's picture, light has no mass, and things with no mass should not be affected by gravity. A beam of starlight passing near the Sun should travel in a perfectly straight line, undeflected. But Einstein's picture was different. Light follows geodesics through spacetime, and if spacetime is curved near the Sun, then light passing near the Sun should follow that curvature. The geodesic near a massive object is not a straight line. It is a curve. Einstein calculated exactly how much starlight passing near the Sun should be deflected. The answer was 1.75 arc seconds. If you could see stars that appeared very close to the Sun's edge, they should appear to be shifted from their true positions by about 1.175 arc seconds, about 0.005 of a degree. But there was a problem. You cannot see stars near the Sun. The Sun is too bright. Its glare overwhelms everything, unless, of course, the Sun's light is blocked. On May 29, 1919, a total solar eclipse would occur. The Moon would pass directly in front of the Sun, blocking its light and revealing the stars beyond. And the Sun, on that particular day, would be positioned in front of a dense cluster of stars called the Hyades. It was a perfect opportunity. The English astronomer Arthur Eddington organized 2 expeditions. One went to the island of Principe, off the west coast of Africa. The other went to Sobral, in northern Brazil. Both teams carried telescopes, cameras, and photographic plates. Their mission was to photograph the stars near the Sun during the eclipse, then compare those photographs to images of the same stars taken months earlier when the Sun was elsewhere in the sky. The day of the eclipse, the weather was terrible. On Principe, A thunderstorm raged through the morning, and clouds threatened to obscure the entire event. But just before totality, the sky began to clear. Eddington managed to take 16 photographs, though only 2 were usable due to the remaining clouds. In Sobral, the weather was better, and the team obtained clearer images. When Eddington returned to England and analysed the plates, measuring the positions of the stars with painstaking precision, he found the answer. The stars were shifted by an amount matching Einstein's prediction, not Newton's. The announcement came on November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The Astronomer Royal, Frank Dyson, declared that the observations confirmed Einstein's theory. J.J. Thomson, the president of the Royal Society and discoverer of the electron, called it one of the highest achievements of human thought. The next day, the London Times headline read, "Revolution in Science. New theory of the universe. Newtonian ideas overthrown." Einstein became the most famous scientist in the world overnight, and the idea that gravity is a force pulling objects through space began its long, slow death. In the century since Eddington's eclipse, Einstein's theory has been tested with ever-increasing precision, and it has passed every test, without exception, without fail. In 1959, Robert Pound and his graduate student, Glenn Rebka, performed an experiment at Harvard University. They placed a source of gamma rays at the top of a 22.6-meter tower and a detector at the bottom. According to Einstein, the gamma rays should be blue-shifted as they fell, gaining energy as they dropped into the stronger gravitational field at the tower's base. The effect was tiny, a fractional change in frequency of about 2.5 parts in a million billion. But the Pound-Rebka experiment detected it, confirming Einstein's prediction to within 10%. In 1964, the physicist Erwin Shapiro proposed what he called the fourth test of general relativity. If space-time is curved near massive objects, then radar signals passing near the Sun should take slightly longer to make a round trip than they would in flat space. Not because the signals are slowing down, but because they are traveling a longer path through curved space-time. When the Earth, Sun, and Venus are aligned, with the Sun between Earth and Venus, a radar pulse bounced off Venus and back should be delayed by about 200 microseconds. Shapiro tested this prediction using the MIT Haystack radar antenna in 1966 and 1967, bouncing radar signals off Venus and Mercury when they passed behind the Sun. The measured delay matched Einstein's calculations. Later measurements, using spacecraft like Cassini, have confirmed the effect to better than 1 part in 100,000. In 2004, NASA launched Gravity Probe B, carrying 4 of the most perfect spheres ever manufactured by human beings. Each gyroscope was a fused quartz ball about the size of a ping-pong ball, polished to within 40 atomic layers of perfect roundness, coated with a thin layer of superconducting niobium. These gyroscopes were designed to test 2 predictions of general relativity. The first was the geodetic effect, the warping of space-time by Earth's mass. A gyroscope orbiting Earth should see its spin axis slowly rotate, dragged around by the curvature of space-time. Einstein's equations predicted a rotation of about 606 milliarcseconds per year. The second was frame dragging, the twisting of space-time by Earth's rotation. A massive spinning body does not just curve space-time, it drags it around with it, like a spoon stirring honey. This effect should cause an additional rotation of about 39 milliarcseconds per year. The experiment ran for 17 months, collecting over 1 terabyte of data. The analysis took years, complicated by unexpected torques on the gyroscopes. But in May 2011, the results were announced at a press conference at NASA headquarters. The geodetic effect was measured at 6,601.8 plus or minus 18.3 milliseconds per year. The frame dragging effect was measured at 37.2 plus or minus 7.2 milliseconds per year. Both matched Einstein's predictions within experimental error. Francis Everett, the principal investigator who had devoted over 40 years of his life to the experiment, could finally say with certainty, Einstein survives. But the most spectacular confirmation came on September 14th, 2015, at 5:51 in the morning Eastern Daylight Time. Two detectors, one in Livingston, Louisiana, and one in Hanford, Washington, simultaneously registered a signal. The detectors were L-shaped, with arms 4 kilometers long. Laser beams bounced back and forth along those arms, precisely measuring the distance between mirrors at the ends. If anything stretched or squeezed the arms, the lasers would detect it. And on that September morning, something did. The signal was a ripple in space-time itself, a wave propagating outward from a cataclysm that had occurred 1.3 billion years ago, when the Earth was covered in single-celled organisms and complex life was still hundreds of millions of years in the future. Two black holes, each about 30 times the mass of our Sun, had been spiraling toward each other for billions of years, slowly losing energy by radiating gravitational waves. In the final seconds, they circled each other hundreds of times per second, approaching half the speed of light. And then they merged, becoming a single black hole of about 62 solar masses. The missing mass, equivalent to about 3 suns, did not vanish. It was converted into energy, pure energy. According to Einstein's E equals mc squared, 3 solar masses of energy is an almost incomprehensible amount. In that final fraction of a second, the merging black holes released more energy than all the stars in the observable universe combined. But this energy did not emerge as light. It emerged as ripples in the fabric of space-time. Gravitational waves, spreading outward at the speed of light, stretching and squeezing space itself as they passed. Einstein had predicted gravitational waves exactly 100 years earlier, in 1916. But he did not believe they could ever be detected. The waves were too weak. By the time they reached Earth, after traveling for 1.3 billion years, they stretched and squeezed the LIGO detector arms by less than 1/10,000th the diameter of a proton. That is a distance smaller than an atomic nucleus. That is a distance smaller than anything humans had ever measured in the history of our species. But LIGO measured it. The signal arrived first at Livingston, then at Hanford 7 milliseconds later, exactly the time it would take a wave traveling at light speed to cross the distance between the two detectors. The waveform matched the predictions of general relativity perfectly, a chirp rising in frequency as the black holes spiraled closer, then cutting off abruptly at the moment of merger. On February 11th, 2016, the discovery was announced. Space-time is a physical thing. It can ripple, wave, and vibrate. And when massive objects spiral together and merge, they send those ripples propagating across the cosmos like waves on a pond. Rainer Weiss, Kip Thorne, and Barry Barish, the scientists who led the LIGO project through decades of development, received the Nobel Prize in Physics in 2017. But the true prize was knowledge, the confirmation that Einstein was right, that space-time bends, stretches, ripples, and curves, that gravity is geometry, not force. If you are still finding this difficult to accept, you are in good company. The idea that gravity is not a force feels deeply wrong. Every instinct we have screams that we are being pulled toward the earth. When you drop something, it falls. When you jump, you come back down. How can this not be a force pulling? Let me try to make it concrete. Let me tell you exactly what happens when an apple falls from a tree. In Newton's picture, the apple is at rest in the tree. It hangs from a stem, motionless. Then, when the stem breaks, a force called gravity begins pulling the apple downward. The apple accelerates toward the ground. Its velocity increases from zero, growing larger with each passing moment, until the apple hits the earth. In Einstein's picture, the apple was never at rest in the sense Newton meant. Even while hanging from the tree, the apple was being accelerated. The branch was pushing it, applying a constant force to hold it in place against the curvature of space-time. The apple was not in free motion. It was being actively prevented from following its natural path. When the stem breaks, that restraining force disappears. The apple, finally free, begins to follow its geodesic, its natural trajectory through curved space-time. From the apple's own perspective, it is not being pulled. It is simply floating, drifting, falling freely along the path that the geometry of the universe prescribes. And the ground, which is still being pushed upward by all the solid matter beneath it, rushes up to meet the apple. This is not just a different way of describing the same thing. It is a fundamentally different physical picture, and the difference has experimental consequences. Consider this. If Newton were right, gravitational mass and inertial mass should be completely independent properties. Gravitational mass is what determines how strongly gravity pulls on you. Inertial mass is what determines how hard it is to accelerate you. There is no obvious reason these two quantities should be related, but they are. They are always identical. Every experiment ever performed has shown that gravitational mass and inertial mass are the same, to as many decimal places as we can measure. Newton noticed this coincidence, but could not explain it. It was just a fact, a mysterious equality with no underlying reason. Einstein explained it. The equality is not a coincidence at all. Gravitational mass and inertial mass are the same because gravity is not a force. When you fall, you are not being accelerated by any force. You are following your natural motion through curved space-time. There is no gravitational force to resist. Your inertial mass is irrelevant to your trajectory. Everything falls the same way because everything is simply following geometry. This is called the equivalence principle. It is the foundation of general relativity. Einstein elevated it from a puzzling coincidence to a deep truth about the nature of reality. If a person falls freely, they will not feel their own weight. Falling is the natural state. Being held up, prevented from falling by the solid ground beneath your feet, that is acceleration. That is force. That is what you feel as weight. Now I want you to think about what this means for your everyday life. I want you to realize that you are already living with the consequences of Einstein's discovery. Whether you know it or not, your phone has a GPS receiver. That receiver communicates with satellites orbiting about 20,000 kilometers above the Earth. By measuring the precise arrival times of signals from multiple satellites, your phone calculates your position to within a few meters. But those time measurements must be extraordinarily precise. Light travels at about 300,000 kilometers per second. If your phone's timing is off by even 1 microsecond, 1/1,000,000th of a second, your calculated position could be wrong by 300 meters. The satellites are moving fast, about 14,000 kilometers per hour. According to special relativity, their clocks tick more slowly because of their velocity. The effect amounts to about 7 microseconds per day. Left uncorrected, this would cause your GPS position to drift by about 2 kilometers per day. But the satellites are also higher in Earth's gravitational field. Space-time is less curved at their altitude. Time flows faster there than on the ground. According to general relativity, this effect amounts to about 45 microseconds per day in the opposite direction. The two effects partially cancel, but not entirely. The net result is that GPS satellite clocks gain about 38 microseconds per day relative to clocks on Earth's surface. 38 microseconds per day. If the engineers who designed GPS had ignored Einstein, if they had pretended that time flows at the same rate everywhere, the position errors would accumulate at about 11 kilometers per day. Within a week, your GPS would be placing you in the wrong city. Within a month, on the wrong continent. Every time you use Google Maps, every time you hail an Uber, every time an airplane lands using satellite guidance, every time a package is tracked across the country, you are relying on Einstein's theory of curved space-time. Gravity is not a force, it is geometry, and that geometry affects the flow of time itself. Let me take you deeper into what Einstein discovered, because there is a question you might be asking, a reasonable, important question. If the ground is pushing me up, why does it not push me off the planet? If the floor is constantly accelerating upward, why is the Earth not expanding like a balloon? Why do people in Australia who are being pushed upward in the opposite direction from people in England not fly apart from each other? The answer lies in the nature of curved space-time, and it is subtle. The floor is accelerating you locally, in your immediate vicinity, but the geometry of space-time curves around the Earth. Different points on Earth's surface are being accelerated in different directions, all outward from the center. But space-time itself is curved in such a way that these outward accelerations do not cause the Earth to grow. Think of it this way. On a flat piece of paper, if you drew arrows pointing outward from a central point, those arrows would diverge. Objects following those arrows would move apart. But the geometry near Earth is not flat. It is curved, and in curved geometry, arrows that point outward from a sphere do not diverge in the same way. The curvature of space-time counteracts the divergence. The very same curvature that creates the impression of gravitational attraction is what allows solid objects to exist, to hold together, to resist being torn apart by the accelerations required to keep their atoms on non-geodesic paths. This is profound. The universe is self-consistent in a way that Newtonian physics never fully explained. The geometry of space-time, the curvature caused by mass, creates a situation where objects can exist, can have structure, can resist falling. The mathematics works out. The physics is consistent. But there is something even stranger, something that strikes at the heart of what it means to exist in this universe. Consider the concept of inertial motion. In physics, inertial motion means moving in a straight line at constant speed, with no force acting on you. In the absence of any force, Newton said, an object will either remain at rest or continue moving in a straight line forever. But here is the problem. There is no such thing as a straight line in curved space-time. Near any massive object, space-time is curved. And in curved space-time, the concept of a straight line must be replaced with the concept of a geodesic, the straightest possible path. On the surface of a sphere, for instance, the straightest possible paths are great circles. They are not straight in the Euclidean sense, but they are as straight as you can get on a curved surface. In the curved space-time near Earth, the geodesics are the paths of free fall, the paths of objects that are not being pushed or pulled by any non-gravitational force, the paths of astronauts floating in the space station, of apples falling from trees, of satellites orbiting overhead. These paths are not straight lines through three-dimensional space. They curve, they arc, they spiral, but they are the straightest paths through four-dimensional space-time. They are inertial motion, in the deepest sense of the term. And here is the unsettling implication. If geodesic motion is the natural state, and geodesic motion near Earth means falling, then being held in place on Earth's surface is not natural. It is forced. It is accelerated. Every object on Earth that is not in free fall is being continuously accelerated. You, right now, are being accelerated. Your body is experiencing a force, not from gravity pulling down, but from electromagnetic forces in the atoms of the floor pushing up. Your entire life, you have existed in a state of continuous acceleration. Every moment since your birth, except for brief instants when you were jumping or falling, you have been deviating from your natural path through the universe. That is what weight is. That is what gravity feels like. The feeling of being constantly, relentlessly pushed away from where the universe wants you to go. There is a famous thought experiment that Einstein used to explain the equivalence principle. Imagine you are in a closed box with no windows. You feel a force pressing you against one wall of the box. You feel exactly as heavy as you would standing on the surface of the Earth. Can you tell from inside the box whether you are on Earth's surface, held in place by gravity, or in deep space, being accelerated by a rocket engine? The answer is no. You cannot tell. The two situations are physically identical. There is no experiment you could perform inside the box that would distinguish between gravitational attraction and acceleration. This is not just a thought experiment. It has been tested. Astronauts on the space station experience weightlessness because they are in free fall, even though they are still deep in Earth's gravitational field. Conversely, astronauts in a spinning space station would feel artificial gravity, weight pressing them against the outer wall, even in the absence of any massive object nearby. The equivalence principle says that gravity and acceleration are the same thing, not just similar, not just hard to distinguish, the same, physically identical, indistinguishable by any experiment. And if they are the same thing, then gravity is acceleration. Standing on the ground is acceleration. Your weight is the force required to accelerate you away from free fall. This is not a metaphor. This is not a different perspective on the same phenomenon. This is a different physical reality, confirmed by experiment, consistent with all observations, more accurate than the Newtonian picture it replaced. Now, let me tell you about an experiment that demonstrates something even more remarkable, something that shows how deep the connection between gravity and time really goes. In 1976, NASA launched Gravity Probe A. This was not the same as Gravity Probe B, which tested frame dragging. Gravity probe A was simpler. It carried a hydrogen maser clock, one of the most accurate atomic clocks then available, to an altitude of about 10,000 kilometers. At that altitude, far from Earth's surface, time runs faster. Not because there is less gravity in some simplistic sense, but because space-time is less curved. The clock in space, following its geodesic, experiences time differently than clocks on the ground. The gravity probe. An experiment measured this difference. Over the course of the flight, which lasted about 2 hours, the space-based clock gained time relative to identical clocks on Earth. The amount gained matched Einstein's predictions to within 70 parts per million. This was not a measurement of some abstract quantity. This was a measurement of time itself. The seconds ticking by on the spacecraft were genuinely, physically longer than the seconds ticking by on Earth. An observer on the spacecraft aged more during those 2 hours than observers on the ground by a tiny but measurable amount. Time dilation is real. It is not an illusion. It is not a matter of perception or definition. Clocks in different gravitational environments run at genuinely different rates, and this affects everything from GPS navigation to the aging of astronauts to the fundamental physics of the universe. Here is another way to think about why objects fall, why apples drop from trees, why you would accelerate toward the ground if the floor suddenly disappeared beneath you. In special relativity, objects always move through space-time at the speed of light. Always. Every object. You, me, the Earth, a photon of light. We are all moving through four-dimensional space-time at exactly the same speed. The speed of light. But this speed is divided between motion through space and motion through time. If you are standing still in space, all of your motion through space-time is motion through time. You are racing into the future at the speed of light. If you start moving through space, some of your space-time motion gets redirected. Less of it goes into time, more goes into space. This is why moving clocks run slow. They have less motion to spare for time. Now, what does space-time curvature do? It tilts the time direction. Near a massive object, the time direction is no longer pointing straight ahead. It is tilted slightly toward the massive object. And since you are always moving through space-time at the speed of light, and since the time direction is now tilted toward the Earth, you find yourself drifting toward the Earth. Not because a force is pulling you, but because the direction of time itself is pointing that way. This is perhaps the most mind-bending aspect of general relativity. Gravity is not a force pulling you through space. Gravity is a tilting of time, and you are always moving through time, so you inevitably drift in the direction that time is tilted. When you stand on the ground, the floor prevents you from drifting. It accelerates you, pushing against the tilted geometry of space-time, keeping you from following the time-tilted geodesic that would carry you toward Earth's center. Your weight is the price of staying in place when time itself is trying to carry you somewhere else. There is a philosophical dimension to all of this that deserves attention. For centuries, humanity believed that gravity was an attraction, a pull, a force reaching across the void to connect massive objects. This belief was not just scientific, it was metaphorical. It shaped how we thought about the universe. Gravity was something that brought things together. Stars pulled on planets, planets pulled on moons. The sun held the solar system in its grip. The language of gravity was the language of connection, of relationship. of mutual attraction. Einstein's picture is different. In general relativity, there is no reaching across. There is no connection between distant objects. There is only local geometry. Each point in space-time has a curvature, determined by the distribution of mass and energy nearby. Objects respond to the local curvature, following their geodesics, but they do not reach out to distant masses. They do not pull or get pulled. The Sun does not hold the Earth in orbit. The Sun curves space-time in its vicinity, and the Earth, millions of kilometers away, follows the geodesic through that curved space-time. The Earth does not feel the Sun. It feels the geometry of space-time where it is. This is a profoundly different picture of the universe. Less romantic, perhaps, less connected, but more accurate, more true to how the cosmos actually operates. The universe is not held together by invisible ropes of attraction. It is shaped by geometry, and we, small beings on a small planet, move through that geometry according to rules we are only beginning to understand. I have spent this entire time telling you that gravity is not a force, but I should be precise. In general relativity, gravity is not a force in the same sense that electromagnetism or the nuclear forces are forces. It does not accelerate objects through space. It curves the space-time through which objects move. But there is a sense in which gravity still acts on you. The curvature of space-time creates the conditions that require forces to keep you from falling. The electromagnetic forces between atoms, the forces that hold solid matter together, the forces that prevent your body from passing through the floor. These are doing real work against the curvature of space-time. So gravity is real. The effects of mass on space-time are real. The curvature that shapes your geodesic is real. What is not real, or at least not accurate, is the picture of gravity as a force pulling on you from the center of the Earth. The Earth's mass is not reaching out and tugging on your atoms. The Earth's mass is curving the space-time you occupy, tilting the direction of time, shaping your natural path through the universe. And the floor is exerting a force on you, accelerating you away from that natural path. This distinction matters. It matters for precision. It matters for predictions. It matters for understanding the true nature of the universe. And it matters for how you think about your own existence. You are not being pulled toward the Earth. You never have been. Every sensation of weight you have ever felt, from the moment you were born until this very second, has been the floor pushing you up, the chair accelerating you away from free fall, the solid matter of the Earth resisting your natural motion through curved space-time. Falling is not accelerated motion. Standing still is. Weightlessness is not the absence of gravity. It is the presence of freedom. And gravity itself, this thing we have named and studied and feared and celebrated for centuries, is not a force reaching across space. It is the shape of space itself, curved by the presence of mass, guiding all motion through its geometry. That contradicts your direct experience. You feel your weight right now. You feel pressure against your feet, against your back, against whatever part of your body is touching a surface. That sensation feels like gravity pulling you down. But that sensation is your nerves detecting acceleration. Your body evolved to feel acceleration. When a car speeds up, you feel pushed back into your seat. When an elevator starts moving upward, you feel pressed into the floor. When you spin around quickly, you feel flung outward. And when you stand on the Earth's surface, you feel pressed into the ground. not because something is pulling you down, but because something is pushing you up. The ground, the floor, the chair, the solid matter of the earth, held together by electromagnetic forces between atoms, accelerating upward against the curvature of space-time. Your nerves cannot tell the difference between gravity pulling you down and the floor pushing you up. The sensations are identical. Einstein realized this. He called it the equivalence principle, and he built an entire theory of gravity on the insight that the two situations are physically indistinguishable. If you want to feel what the universe actually intends for you, if you want to experience your natural state, all you need to do is jump. For a fraction of a second after your feet leave the ground, before you hit anything else, you will be in free fall. You will be following your geodesic. You will be weightless, truly weightless, feeling no force at all. And then the floor will rush up and catch you, beginning once again to accelerate you upward against the geometry of the cosmos. That brief moment of freedom, that instant of weightlessness, is your natural state. Standing on the ground, feeling the weight of your body, feeling the pressure of the floor against your feet. That is artificial. That is acceleration. That is force. Let me tell you about an experiment that makes this concrete. In 2010, a team at the National Institute of Standards and Technology in Boulder, Colorado, performed one of the most precise measurements of gravitational time dilation ever made. They used 2 optical atomic clocks, among the most accurate timekeeping devices ever constructed. These clocks lose or gain only about 1 second in several billion years, and they placed these clocks at different heights, separated by only about 1/3 of a meter. 1/3 of a meter, about the length of a ruler, and they measured a difference in the rate of time. The clock that was higher, closer to space, farther from Earth's center, ran slightly faster. The difference was tiny, a few parts in 10 to the 18th power, but it was measurable, and it matched Einstein's prediction exactly. Time flows differently at different heights, not metaphorically, actually. A clock in your attic runs faster than a clock in your basement by an amount that is now measurable. The curvature of space-time is real, tangible, detectable. In 2024, another team at GILA, a joint institute of NIST and the University of Colorado, pushed this even further. They used an optical lattice clock to measure gravitational time dilation at the sub-millimeter scale, about the thickness of a human hair. Time flows at measurably different rates, over distances smaller than the width of a fingertip. This is what space-time curvature means. This is why gravity is geometry, not force. Mass curves space-time. Curved space-time means different flow rates of time. Different flow rates of time mean different geodesics. Different geodesics mean different paths for freely falling objects. No pulling required, just geometry, just mathematics, just the shape of the universe itself. So where does this leave you? Right now, sitting in your chair, feeling the weight of your body, the pressure of the seat against your back, it leaves you with a choice in how you understand yourself. You can continue to think of gravity as a force pulling you down. Most people do. Most people will live their entire lives with the Newtonian picture in their heads, and it will serve them well enough. Newton's equations still work for almost all practical purposes. They are simpler to calculate. They match our intuitions. Or you can embrace the stranger, more accurate picture. You can recognize that you are not being pulled anywhere. that the chair beneath you is accelerating you upward, pressing against your body, fighting against the natural curvature of space-time that would carry you toward the Earth's center. You can recognize that when you stand up, you are not lifting yourself against a force. You are simply allowing the floor to push you into a different position. And when you sit back down, you are not falling. You are briefly entering a natural state of motion, following a geodesic, before the chair intercepts you and begins accelerating you again. You are never truly at rest. Not in the deep sense. Not in the sense that matters to physics. You are always either falling freely through curved space-time or being accelerated away from that natural path. There is no in-between. There is no standing still. There is only geometry and your motion through it. I want to end with a question. The question that Einstein's discovery forces us to confront. What else have we been wrong about? If humanity could be mistaken about something as fundamental as gravity, something we experience every moment of every day, something we have studied for 3 centuries, what other beliefs might be illusions? What other certainties might be comfortable lies? We believed the Earth was the center of the universe. We were wrong. We believed time flowed at the same rate everywhere. We were wrong. We believed space was a fixed stage on which events play out. We were wrong. We believed gravity was a force that pulls. We were wrong. Science is the process of finding out what we are wrong about and replacing it with something closer to the truth. It is an endless refinement, an eternal approach toward accuracy that never quite arrives at absolute certainty. Einstein's general relativity has survived a century of tests, but even Einstein knew his theory was incomplete. General relativity is incompatible with quantum mechanics, the other great pillar of modern physics. The 2 theories cannot both be fully correct. Something must give. The next great revolution in physics, whenever it comes, may overturn Einstein, just as Einstein overturned Newton. We may discover that space-time itself is not fundamental, that it emerges from something deeper, something stranger, something we cannot yet imagine. But that future discovery, whatever it turns out to be, will not make Einstein wrong in the way Newton was wrong. It will not bring back the force of gravity. It will extend and deepen our understanding of geometry, of space-time, of the fabric of reality. The universe is stranger than we know, stranger than we can imagine, but not stranger than we can discover. Newton looked at a falling apple and saw a force reaching across empty space. Einstein looked at a falling apple and saw something different. He saw an apple following the straightest possible path through curved geometry. He saw a universe where mass warps space-time and space-time tells mass where to go. He saw a reality where falling is natural and being held up is an interference. Both men looked at the same apple, but only one of them saw the truth. The next time you feel your weight, the next time you notice the pressure of the ground beneath your feet, remember what you are actually feeling. You are feeling the floor accelerating upward. You are feeling solid matter, held together by electromagnetic forces, pushing against you. You are feeling the intervention that prevents you from taking your natural path through the curved space-time around you. You are not being pulled down. You are being pushed up. And if you want to feel what the universe actually intends for you, all you have to do is let go and fall. For that brief moment before something catches you, you will be following your true path, your geodesic, the straightest line through the curved four-dimensional geometry of existence. You will be weightless. You will be free. You will be, for that fleeting instant, in your natural state. And then the ground will push you again. Gravity is real. The curvature of space-time is real. The equations that Einstein wrote in 1915 describe something profound and true about the nature of reality. But gravitational pull, that is just a very old, very persuasive, very beautiful lie. And now, you know the truth. Before I let you go, there's one more thing I want you to consider. One more implication of Einstein's discovery that reaches beyond physics into the fabric of human experience. For most of human history, we believed we were special. We stood at the center of the universe. The sun, the moon, the stars, all revolved around us. We were the purpose of creation, the reason everything existed. Then Copernicus told us we were not at the center. We were on a planet orbiting the sun. Then astronomers told us the sun was just one star among billions in a galaxy. Then they told us our galaxy was just one among hundreds of billions in the observable universe. Our cosmic significance shrank with each discovery. Einstein's revolution continued this deflation, but in a subtler way. We believed we were standing still, firmly planted on solid ground, masters of our own position. We believed we were at rest while the rest of the universe moved. But Einstein revealed that we are not at rest. We are being accelerated constantly, every moment. The ground beneath our feet is doing work, pushing against us, fighting against the natural geometry of the universe. We are in a constant state of struggle against the curvature of space-time. We are not standing still. We are being held in place. There is a difference. And the moment that holding stops, the moment the floor gives way, we do not fall. We do not accelerate. We simply begin to follow our natural path, the path the universe has laid out for us, the geodesic through curved space-time that leads inevitably toward the center of mass. There is something humbling about this, and something liberating. We are not masters of our position. We are riders on a curved geometry, held in place by the accidents of solid matter and electromagnetic forces. The universe does not care about our comfort. It does not care about our sense of up and down, our feeling of stability, our illusion of standing still. It simply is what it is. A curved, dynamic, expanding geometry in which everything moves, everything changes, everything falls. One final thought. Every physicist who has ever grappled with general relativity has felt something strange when they truly understood it. A kind of vertigo, a disorientation, the feeling of having the ground pulled out from under them, metaphorically and, in a sense, literally. You may be feeling something like that now. If you have followed this argument, if you have really understood what Einstein discovered, you may be looking at the floor beneath your feet differently. You may be noticing, for the first time, the pressure against your body, the sensation of being pushed. That sensation was always there. You just never noticed it because you interpreted it wrong. You thought it was gravity pulling you down. It was the floor pushing you up. The universe has not changed. The laws of physics have not changed. The floor was always pushing you up. You just did not know it. And now you do. What you do with that knowledge is up to you. You can ignore it, return to the comfortable Newtonian picture, pretend that gravity is a force, and get on with your life. That is fine. Newton's equations still work well enough for almost everything you will ever do. Or you can carry this knowledge with you. You can remember every time you feel your weight that you are experiencing acceleration, that you are being pushed, that the natural state of the universe is free fall, and everything else is an interference. You can look up at the stars and remember that the light from those stars was bent by the sun's gravity, deflected by the curvature of space-time, arriving at your eyes from a slightly different direction than you might expect. You can think about the satellites overhead, their clocks ticking faster than yours, their orbits shaped by the geometry of the cosmos. You can remember that the universe is stranger than Newton ever imagined, that space and time are woven together into a single fabric. That mass curves this fabric, that motion follows the curves. And you can remember that the most familiar sensation in human experience, the feeling of your own weight, is a lie. Not a malicious lie. Not a lie anyone told you on purpose. Just a misunderstanding. A confusion between pulling and pushing, between falling and standing still, between force and geometry. A very old, very persuasive, very beautiful lie. Newton gave us equations that worked. Einstein gave us understanding of why they work. The next great physicist, whoever they are, wherever they are, will give us something even deeper. A theory that unifies gravity with quantum mechanics. A theory that explains what space-time actually is. A theory that reveals the next layer of reality. Science never ends. Understanding never stops. Every answer opens new questions. Every discovery reveals new mysteries. But for now, in this moment, you know something that Newton did not know. You understand something about the universe that puzzled humanity for centuries. You see, with clarity, a truth that Einstein spent 8 years struggling to discover. Gravity is real, but gravitational pull is not. And the floor beneath you, right now, this very second, is pushing you upward against the curved geometry of space-time. Feel it. That is reality. That is physics. That is the universe telling you how it actually works. Welcome to Einstein's cosmos. It is stranger than you ever imagined, and far more beautiful than Newton's universe could ever be.